Hello! Today we're doing an extension off of 6.7, which is about recursively defined sequences. Now I know hearing that you're probably all thinking, oh awesome, great, I have absolutely no idea what any of those three words meant. But hopefully by the end of this it won't seem so terrible. We were already writing what are called explicit sequences, which if we can kind of just go back to that for a second, the explicit equation for an arithmetic sequence that we had used before was our term that we're looking for, a sub n, will be equal to the first term, a sub 1, plus, in parentheses, n minus 1 times the common difference. And for a geometric sequence, we were looking at an explicit equation that looked like a sub n equals that first term, a sub 1, times a common rate raised to the n minus 1. Okay, so the explicit equations for the sequences here and here were all basing the next terms in the sequence on the first term, a sub 1. So it's an equation that bases every other term on the first term. Now the difference between these explicit equations and the recursive equations we're going to do today is that the recursive doesn't base it upon the first number of the sequence, but rather the previous number. So if I'm looking for the 26th term, my equation is going to be based on the 25th. Alright, so my equation is basically telling me you can get any number you want as long as you know the number before it. Whereas my explicit ones were saying you can get any number you want based upon the first number in the sequence. Alright, so let's take a look here. We have a recursive equation for an arithmetic sequence, which is saying that any number that you want can be found by taking the number that came before it and adding the common difference. And we kind of knew that already. Now, a recursive equation for a geometric sequence is saying you can get any number you want by taking the number that came before it, multiplying it by the common ratio. Now, hopefully that's almost clicking in your head like, wow, that seems way too easy. So let's just take a look at how it works, and let's just use them first of all before we start to try and write our own. What we want to do here is write the first 6 terms in each of these sequences. The first one is going to be an arithmetic recursive sequence. The second one's going to be a geometric. So what this has here is our first term of 2, and then after that, any term that comes after it, like let's say I want a sub 2, this is a sub 1, I want the next term, a sub 2 is going to equal a sub n minus 1, so if n here is a 2, that's going to be a sub 1 plus a common difference of 3. So that means 2 plus 3 equals 5. Now if I want a sub 3, I want the third term, what's it going to look like? It's going to look like a sub n minus 1, in this case n is a 3, so n minus 1 is a 2, so I'm looking at the second term, plus the common difference, equals 5 plus 3 equals 8. And next, if I want the fourth term, that's going to be, if you're catching on to the pattern here, a sub 3 plus the common difference, which equals 8 plus 3, which equals 11. A sub 5 equals, well, I went a sub 1, a sub 2, a sub 3, a sub 4, plus the common difference, which equals 11 plus 3, which equals 14. And lastly, a sub 6, which is going to equal a sub 6 minus 1, which is a sub 5, plus the common difference of 3, which will equal 14 plus 3, which equals 17. Okay, so if I go down and I'm looking at all of my solutions, the first term is a 2, second term 5, 8, 11, 14, 17. And just to reiterate, I've taken one term with a common difference of 3. So 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, 11 plus 3 is 14, 14 plus 3 is 17. So it looks like my sequence is working correctly. And this is how I would recursively define it. Okay? Now let's look at a geometric example. It's first saying that my a sub 1 term equals 1. So easy enough. I have one term. I only needed 6, so I'm almost got a good start at least. Now if I want to go to a sub 2. Well, this tells me that if I want n to be 2, I want a sub 2, that I have to do 3 times the previous term. In this case, if n was a 2, then that's a sub 1. So this tells me that I need to do 3 times a sub 1, which equals 3 times 1, which equals 3. Now if I want a sub 2, then that's equation tells me that I need to do 3 times the previous term, which if I wanted a sub 2, I'm sorry, a sub 3, should be 3. If I wanted a sub 3, then I need the previous term to multiply by. And I just found out that was a 3. A sub 2 equals 3 times 3, which equals 9. Now if I want a sub 4, that means that I'm doing 3 times the previous term, a sub 3, which I just found out was a 9, so 3 times 9, which equals 27. A sub 5, which is going to equal 3 times the previous term, a sub 4, which is going to be 3 times I just found out. A sub 4 was 27. 3 times 27, getting a little bit high, but hopefully you still know that one to be 81. And a sub 6, which is going to be 3 times the previous term, a sub 5, which I just found out was an 81. 3 times 81, this one might take you a little bit, but it's 243. Alrighty, and just to reiterate again, I have my first number, I wanted the highlighter there. First number is a 1, my first term. And then what this recursive definition tells me is that I have a common ratio of 3. So that means I should be multiplying by 3 every time. 1 times 3, 3. 3 times 3, 9. 9 times 3, 27. Times 3, 81. Times 3, 243. So I've definitely done this correctly. And this is how I would recursively define it, basing any number off of the previous number. Now let's take a look at what these look like graphed. So here I have an arithmetic sequence. So we should be able to think, I know arithmetic sequence relates to linear. So when I graph these points, I should get a line. And here in B, I'm looking at a geometric sequence. So I should be looking at some sort of exponential curve. Alright, so I've marked these and scaled them appropriately for what I'm going to be doing. And I want to graph my first arithmetic sequence. My first term is a 2. I'm going to put a dot right around where a 2 is. My second term is a 5. I'm going to put a dot right around where a 5 is. Third term is an 8. Continuing. Oops. Fourth term is an 11. Fifth term is a 14. And sixth term is a 17. So, what does that look like to you? Well, just like we were hoping, it turns out to be a pretty straight linear equation, which it should be. You have an arithmetic sequence there. It should be going up at a common difference. That common difference is much like the slope. So now if we go over to our geometric sequence, we're hopefully looking for an exponential curve here. So let's hope for that. 1 is a 1, which is way down here. 2 is a 3, which again is way down here. 3 is a 9, we're getting a little bit higher. 4 is a 27. a little bit higher. 5 is an 81. Whoa, that just shot up. 6 is a 243. That just went way up there. So when we look at how we're going to draw a line through this one, I want a smooth curve, but it just shoots up here. And we are definitely looking at an exponential curve there. So again, we see arithmetic sequence creating a linear curve, regardless of the fact that we're defining it recursively, and a geometric sequence creating an exponential curve, regardless of the fact that we are defining it recursively. Okay. Now what we're going to be doing is actually going between explicit equation to recursive and recursive equation to explicit. So here it might get a little bit jumbled, a little bit more confusing. Before we were kind of just plugging in numbers and seeing how the relationships worked, but now we want to be able to actually work with the equations. So I want to remind you again what the explicit formulas for these things are, which for an arithmetic, the explicit equation is any number that you want can be found by taking the first number, a sub 1, and what we're going to do is multiply that, or add it actually, sorry, by n minus 1 times the common difference. And for a geometric, we can find any number that we want based upon that first number, a sub 1, times a certain rate, common rate, raised to the n minus 1. Okay, so these are the older equations that we were looking at, the explicit equations. And if you need the recursive equations, those are back on the previous page. So what we have in example 3 is we have the recursive rule, and we want to write the explicit equation for it. Okay, so we need to pull relevant information away from this. First of all, we're given the first term. That's going to be crucial when we're writing a sequence in the explicit form. What else are we given? What else is important here? Well, this right here, this negative 10, that's the common difference. Okay, this recursive equation tells me I can get a number by taking the previous number and subtracting 10. That subtraction of 10 is the common difference. So we're given all the information we need, we just kind of have to plug it in now. So a sub n, and this is the explicit form, will equal that first term, 25, plus n minus 1 times the common difference of negative 10. Now remember, all we have to do is distribute. A sub n equals 25 plus negative 10n plus 10. So finally, when we combine like terms, I have a positive 25 and a positive 10. A sub n equals negative 10n plus 35. Not too bad, right? Now let's look over here. Here I have a recursive definition of a geometric sequence. See, I knew over here that this one was explicit. I knew over here that this one was arithmetic because of the form of the recursive definition. Right? I have subtraction of 10. That tells me that there's a common difference. Over here, I have multiplication by negative 0.5. So that tells me that this over here is going to be a geometric recursive definition. So again, let's take a look at what the important information that is given to us is. I have first term, which I need to create the explicit formula, but I also need the rate. And what do you know? It gives me the rate as well. So I'm going to write an equation where I can get any number that I want based upon the first term in the sequence. Not based on the previous term, which is what this recursive rule does, but the first term. So my explicit definition says a sub n will equal the first term, a sub 1, which I know is 19.6, times the rate, which I know, negative 0.5, raised to the n minus 1. And look at that. It's done. This now tells me that I can find any number based on the first number, rather than any number based on the previous number in the sequence. Alright, take a second. If you need to pause that, if you need to rewatch that, go for it, because the next thing that we're going to go into is now doing the exact opposite and taking the explicit forms and writing a recursive rule for the explicit forms. Alright, so if you're not fully set with taking the recursive and putting it into explicit, revisit that. There's even some examples in your book if you want to take a look at those, but make sure that you're solid on that before moving on. Alright, so now what I need from here becomes a little bit different, right? What I want to do is remind us again what the equations for recursive are. Which over here is going to be whatever number that you want equals the previous number, a sub n minus 1, plus whatever the common difference is. And over here, any number that you want will equal the rate times the previous number. Okay, so when I'm looking here, basically all that I need is the common difference, and that's it. When I look over here, pretty much all that I need is the rate, and that's it. So where can I find the common difference right in here? Is there any way that I can kind of pull the common difference out of part A? Let's take a look at what the first few terms of this sequence would look like. That way we can kind of pull out the common difference. If I were to look for the first term, a sub 1, n would be a 1, so that means this is 3 minus 2, the first term is a 1. Well, what about if I look for the next term and I make n equal to a 2? Well, that means that's negative 4 plus 3, negative 1. Okay, let's look at the third term, because I see somewhat of a common difference here, but I don't know if it's common between all of the terms. So the next one I'm going to look at is the third term. That makes negative 6 here, negative 6 plus 3. That means that my third term is a negative 3. So what am I noticing? My terms go 1 to negative 1 to negative 3. What's my common difference? 1 to negative 1 to negative 3. Yeah, it's a negative 2. So if I want to write the recursive rule, I can say that any number will equal the number that preceded it, a sub n minus 1, plus the common difference, which we just said was a negative 2. And that is my recursive definition. I can get the second term by taking the first term and subtracting 2. Is that true? Can I get negative 1 by taking the first term 1 and subtracting 2? Yeah. Can I get the third term by taking the second term and subtracting 2? Yes. Now let's go over to the geometric version. Over here, the only piece of information that I need, as I said before, is the rate. Now how can I find out what the rate is based upon this explicit formula? Well, again, I could do the same thing, and I could look at what some of the first numbers in the sequence are. So if I put in a 1 into here, and I'm looking for the first term, a sub 1, that means that this is 1 minus 1, which is 0, 2 to the 0. Anything to the 0 power is a 1. So my first term is a negative 3. Now, what's my second term? Well, that's going to be a 2 minus 1, which means this is 2 to the first, which means I'm doing negative 3 times 2, which means I have negative 6. Okay, I think that I can see how I can get from negative 3 to negative 6, but I want to get a third term just to be sure that that's common between all of them. So let's try the third term. It's going to be 2 raised to the second power, so that's a 4. 4 times negative 3, that gets me what? Negative 12. So what could be a common factor going from negative 3 to negative 6 to negative 12? Negative 3 to negative 6 to negative 12. Well, I could multiply by 2 here. Negative 3 to negative 6. Does that work for the next time? Negative 6 to negative 12? Yeah. So my rate is a 2. Now I also could have just kind of pulled that out right from this explicit equation, because in the explicit equation the rate is the number that's being raised to the exponent. So that could have been an easy way for me to do that. So when I write my recursive formula, it's going to say that any number that I want equals the rate, which I just found out was a 2, times a sub n minus 1. Not too terrible. And now take a minute, if you need to replay that, pause, do whatever you need to really grasp that. Do that right now. I only have one more thing to show you, and I'm really not even going to show you. It's more of a challenge problem for you all. So right here, stop, take a minute, really bring in this page, really take it and make sure that you understand it. The last thing that I want to look at is a type of sequence right here. And it's not like the other ones that we've seen. It's not like you have this common difference or this common ratio or this common factor. It's a little bit different, like a 1, 1, 2, 3, 5, 8. And this is actually a very, very well-known sequence. It's called the Fibonacci sequence. And what I'd love is for each of you to spend a little bit of time trying to write a recursive rule for this sequence. Okay, it's not going to be specifically like one of the ones that we've done before. This is definitely going to be thinking outside the box and trying something new. But I really love to see who could figure this out. Alright, we will check in this on this in class. Hopefully some of you can do it, because that would just absolutely make my day. But I will see you all later.